All right, so we are talking about volcanic hazards today. So this gives kind of the basic volcanic hazards. Obviously, lava's hot, don't touch it, but it's really not what causes the most cause of life, or it doesn't cause the most deaths. Pyroclastics are very dangerous. Pyroclastics are when there's all that gas and usually that silica type of magma as well, that felsic magma. And you get this big explosion. And then you get this pyroclastic flow, which is like a huge ball of really, really hot gas. And a lot of times it's poisonous gas. You've got sulfuric acid and carbon dioxide, uh, as well as all this ash and cinder blocks and everything just pummeling down the hill super, super fast. So 100 miles or 100 kilometers per hour, 60 miles an hour. You can't outrun this. You can't even really drive out of its path. This is what killed and buried Pompeii, if you've heard of Pompeii. So here's a picture of a pyroclastic flow, super fast, so very dangerous coming down the hill. Here's an aerial view of one, and then here's an aerial view of an ash plume. This is different. It's not coming down the slope of the mountain, but really more up into the atmosphere. And then once it gets up into the atmosphere, it can spread pretty much globally, especially if it gets up into like the stratosphere. And then it can block the sunlight and actually reduce global temperatures. So here's a picture or a diagram of some topographical changes after Mount St. Helens last erupted. So, well, you can see the crater formation. So as the explosion happened, you lose the top of the mountain. The mountain used to have this nice little peak. Now it's a crater. So that whole top has essentially been blown off. As well as all of that material coming at you, you obviously have the lava and any kind of cinder blocks coming down. We have a pumice plain. Pumice is a very light, kind of frothy rock type that comes from extrusive volcanic eruptions. It's kind of light and fluffy because it has has little holes all throughout it that is from the gases escaping during the eruption. It's actually, if you have like a rock where you would exfoliate the bottom of your feet, that is pumice. And so you can see at Mount St. Helens, all that material kind of landed right here in what they have labeled the pumice plain. And we also have landslide deposits. So this is a pretty big mountain, a lot of snow up here. So when the eruption happens, you're melting the snow, you're getting a lot of landslides. And this is where the landslides deposited. They actually think with Mount St. Helens that it was actually a landslide that happened first, which you lose a chunk of the top. Now you don't have as much pressure holding the magma chamber in, and that reduction in pressure is what allowed the eruption to happen. But it was probably going to blow sooner or later regardless. Then it talks about phreatic eruptions. This is when you have a lot of steam in the eruption, so the steam is very explosive. It can be like a boiler explosion, it says here. Again, you're going to find that associated with your subduction zones. And then the secondary effects on climate and atmospheric chemistry, because it can get up into the upper layers of the atmosphere. Here are some pictures of a landslide. We call these lahars. Technically, it's not a landslide, it's a mudslide. And if it's a mudslide associated with a volcanic eruption, we call it a lahar instead of a mudslide. But you can see that these people have suffered a lot of property damage, and none of this is related to lava or pyroclastic flow. This is all from the mud flow. Actually, the Pompeii eruption, if you've heard of it, so Pompeii was hit by the pyroclastic flow. Another nearby town, kind of on the other side of Mount Vesuvius, was covered in a lahar deposit. So just depending on which way things flowed, you have two different towns that were completely destroyed from that eruption. Here, this is talking about the poisonous gases that are associated with volcanoes. This is carbon dioxide. This is showing Mammoth Mountain area in California. And so you have with the magma chamber, you have a lot of gas in here. But then it can kind of creep out through different faults and things, and it can get trapped in the soil and cause the trees to die. And as shown here, it can get trapped in the basement, which would be very hazardous to the people living in this home right here. Also, it can come up through a fault and find its way to a body of water. There's lots of lakes right here. And once it comes to surface, the water is kind of heavy and it doesn't really come through the water. So it builds up at the bottom of the lake until there's so much air pressure or gas pressure that then the lake explodes and then releases all of this carbon dioxide all at once. And so you'll see this around these lakes up there in Mammoth. And so in this picture, I think is actually from a lake explosion, more so than the soil, but really I didn't take the picture, so I don't know when it's from or anything. Here is a chart of the atmospheric effects from some volcanic eruptions. This usually happens with your larger eruptions, and of course it has to have that fine grain material. So this doesn't really happen with that Hawaii basaltic, flowy, oozy kind of eruption. So this was an eruption that happened in June of 1991. This is the amount of aerosols in the atmosphere. So this is pre-eruption. During eruption, you can see it's kind of staying right at that latitude that the volcano sits in. And then by August, it has spread out. And then it's kind of spread globally. And what is this? Is now 2 to 3 years spread globally, but kind of thinned out as well. And if you look at the monthly temperature, when the eruption happened, the Earth cooled pretty much until the end of 93, which would be associated with this picture here, where it's all over, but not really concentrated and not really thick in any one location. We classify volcanoes by activity. We have active, meaning they could go at any minute or they've gone off just recently. Extinct, meaning we don't think they're going to erupt anytime soon. And dormant, which really just means it's sleeping. Like we're not in imminent danger and it hasn't gone off recently, but it could reactivate. They have a volcanic explosivity, cannot say that, explosiveness index from 0 to 8. So this is trying to give a numerical value for how dangerous they think a volcano would be. So we've got the super volcanoes here, the Long Valley Caldera. This is the one with Mammoth Mountain, or right next to Mammoth Mountain, and Yellowstone Caldera, huge. And then like the Hawaii ones would be like way up here, very, very, very low. And what goes into that is the volume of pyroclastics produced, how high they went up into the atmosphere, and how long the eruption lasted. Now, some of these, like Yellowstone, hasn't really gone off in human history. How do we know? We go through and we can see the thickness of the ash layers associated with the Yellowstone eruption, and we can date those to make sure we're looking at ones from a specific eruption. We can chemically tie them back to Yellowstone or to that one volcano. And so the thickness as well as the distance. So the further the ash deposit goes, the higher it went up into the atmosphere. We watch for seismic activity near volcanoes to kind of give us a warning that something might be happening soon. And what we look for is earthquakes and changes in the topography. So as that magma chamber is filling up, you can imagine it's going to shift things around, causing earthquakes. And as it's filling up, it's going to kind of blow up like a balloon. So everything above that balloon is going to kind of tilt or uplift one way or another. Here is an example of that. I think this is LiDAR, but I don't remember exactly how they measured this, but elevation data. And then they come back and they fly sometime later and they measure the difference in the elevation between the two flights. And so colored here, the higher on the scale is more elevation change. And so you can see right around the edge of this caldera here, this is a Hawaiian caldera, it's gained 1.5 centimeters. Where are volcanic hazards in the United States? Predominantly with our subduction zones, which we're going to find Upper California, Oregon, Washington, up around Alaska, as well as we have Hawaii, which we've talked about, and then the hot spots like Yellowstone. This chart here is showing how long ago it has erupted and how many times it's erupted as far as we know. So like this one here, Mount Baker, we only have evidence, or we have only found these ash deposits from this one eruption from this one volcano, but it could have erupted at other times, but either those ash deposits were eroded away, or maybe it was so small it really didn't leave much of a record in the geologic record. Here is a map of the Aleutian Islands. All of these are subduction zone related volcanoes right here. After an eruption, you can get the crater, which is when the top is blown off. You can also get a caldera, which is when the overlying rock material has fallen into the empty magma chamber. So you imagine this, balloon was filled with magma. And then once the eruption happens, the magma empties, and then there's nothing supporting the overlying material, so it all drops down. These calderas can be huge, especially in these super volcanoes like Mammoth and Yellowstone. And you can drive around. I mean, they're just these huge valleys. You don't really even realize you're in it when you're just like driving through, because they're just that big. Here's a map, or a couple maps, showing how far the Yellowstone ash deposits have gone in the past that we have found. And here's one showing how large the magma chamber is right now under Yellowstone. And that is it for volcanoes.